This section is over 6.1b, simplifying radicals. When you work with radicals, we always have a radical sign. Inside the radical sign, this is called the radicand. And right here is called the root. It's also known as the index. So when you have several, right here we have the square root of 48. Here we have the cubed root of 48. And here we have the fourth root of 48. So I like to tell everybody that whenever you have radicands, you are, it takes pairs, it takes however many is here to get a whole one out. So this, since there's nothing here, we have to pretend there's a 2 there. So when we factor this down to all of its prime factorizations, we get 2 goes into that 24 times, goes into that 12 times, goes into that 6 times. And then these here are all the primes that we have for this particular one. So we want groups of pairs. So we're going to take, there's 1, there's 2. So 2 2's come outside, and what 2 times 2 is? 4. And then what's left inside? This lonely guy right here, 3. So the answer to 48, the square root of 48 is 4 to square root of 3. Again, if you do it, this one here, we always have to take, we have to do the primes. And they're the same as before over here. But this time, we need 3 of each factor in order to pull it out. So we have 3 2's here, but we don't have a group of 3 for either one of these. So those, the 2 and the 3 have to stay in. So we have 6 inside the radical, the cube root of 3, and there's just 1 2 that pops out. Now, on the next one, we have 48. Again, we want to do the prime factorizations, which is 2 times 2 times 2 times 2 times 3. Now we need groups, we have to have 4 of each one in order to take 1 out. So if you circle, we have 4 2's that can come out, but we have a 3 that's on the inside. Don't forget to put your root where it belongs and not lose that, because we can't just leave it and go to this, from this to this, because they mean totally different things. This is the fourth root, this is the cubed root. This one here would be wrong if we were trying to find the fourth root of 48. Now let's try and work with some radicals that have variables in them. We have 81, can't see that one very well. We have 81 y cubed to the 6th and the cube root of those. Again, with numbers, we have to find the prime factorization. So we have 81, 3 will go into that 27 times, 3 goes into this 9 times, 3 goes into this 3 times. Index tells us how many that we have to group together to take 1 out. So this one, we have 3 3's, so we can pull 1 3 out, but the other 3 has to stay inside. Now, when you have variables, they're quite easy to do, because all you have to do really is divide the roots. 6 divided by 3 is 2. So just like we have 6 6's here, if you group them by 3's, we actually have 2 that come out, and there's none that's left inside. So this would be our answer. Be careful, because a lot of people will say, okay, all I have to do is divide the exponent by the index to get my answer. They'll sometimes think that all they have to do is divide 81 divided by 3 to get your answer. And that is a mistake. You can do it with the variables, but you cannot do it with the numbers. You have to do the prime factorizations to find out what you can pull out. Let's try another one. This one is 16x to the 15, y to the 5th, and we're going to take the cubed root of those. First thing we do is we look at the number. We have to do the prime, whoops, we have to do the prime factorization, and we can take 2 into that. It was 8. 2 goes into 8 4 times. 2 goes into 4 2 times. Our index tells us how many we have to have in our group, so we have to have 3 in our group. So we can pull 1, 2 out, and the other 2 has to stay in. Now let's look at our x. We have 15 divided by 3 is the whole number, because 5 times 3 is 15. So we can take out 5 x's, but now we have our y has the 5. So if we divide that by 3, we actually get 1 with the remainder of 2. So 1 whole 1 will come out, but we have 2 that stay inside. And that would be our answer for this one. Again, if you wanted to find these out, you could write the 5 y's. And you can say, okay, I've got 3. 1 comes out, 2 stay in. Answers are the same. Let's try this one. 192 y to the 7th to the cubed root. Okay, we do the numbers first by finding prime factorizations, and we see that 2 goes into that 96 times. 2 goes into 96 48 times. 2 goes into 48 24 times. 2 goes into 24 12 times. 2 goes into 12 6 times, and 2 goes into 6 3 times. And we're looking, our index is 3, so we have to have groups of 3 in order to pull them out. So here's one group of 3, and here's another group of 3. So we're actually going to pull 2 3s out, or 2 2s out. And 2 times 2 is 4. We have our cubed root. Now we have 3 is left inside because he's all by himself, lonely guy. Now we have our variable. So we have 7 divided by 3. We can take 2 into that with the remainder of 1. So we can take 2 y's out and 1 y stays in. And that's our answer. Now, sometimes we have fractions inside roots. And when you have a fraction and it's a square root, all you really have to do is you have to square root the number. And then divide the exponent by the root, just like we've been doing. So this particular one, if you take the square root of 16, you get 4. Divide that by 4 by 2, you get x squared. And then divide 4 by 2, you get y squared. And that is your answer. Now let's do one that's just a little bit more complicated. We have 108x to the 15, y to the 15, over 27x to the 10, y to the 3. Oh, and it's in a cubed root. Now, when you have a fraction inside of a fraction, and it's the same root, you can reduce as much as you can inside before you try to take the square root. So this is what we're going to do. 27 actually goes into 108 4 times. And then we can reduce. We have 10 here. If we gives us 5 on the top. And if we take 3 from the top and the bottom, we get 12. So rewriting that, it gives us the cubed root of 4x to the 5th, y to the 12th. Now, we know that the factorization of 4 is 2 and 2. With an index of 3, we only have 2 of them, so we can't pull anything out. So the 4 has to stay inside. Now, looking at our exponents, if you divide it by 3, you get 1. And then subtracting 3 from 5, you get 2. So it has x to the second. And then if you divide 12 by 3, you get y to the 4th. And that would be our answer, because we can't pull anything else out and there's nothing to cancel. All right, our next one is 32 x to the 12th, y to the 6th, and we're going to take the square root of it. Anytime you see a square root, we automatically know that the index is 2. So, first thing that we need to do is to do our prime factorization of 32. 32, 2 goes into that 16 times, 2 goes into 16 8 times, 2 goes into 8 4 times, and 2 goes into 4 2 times. And since we need pairs, we have 1, 2, 2 2's that'll come out, which 2 times 2 is 4, and then 1 2 stays in. Okay, now we want to divide 12 by 2, gives us 6, and that's how many comes out, and divide 6 by 2, we get 3. So this answer is 4 x to the 6th, y to the 3rd, square root of 2. That's all it takes when you're simplifying fractions, is to make sure you get everything that's inside out. Here's another problem. We've got 81 x to the 5th over 16 y to the 6th. And we're taking the square root of that. We could break these apart and make square root on the top and a square root on the bottom. Now all we have to do is, what is the square root of what's inside? Square root of 81 is 9. And then really we want to divide that by 2. So we have 5 divided by 2 is 2 times 2 is 4, with the remainder of 1. So 2 x's will come out, but 1 x has to stay in. Now let's do the bottom. The square root of 16 is 4. And then if you divide, because the index is 2, divide 6 by 2, you get y to the 3rd, which it leaves nothing inside. Always, always, when you pull something out of the top and out of the bottom, look to make sure, does anything cancel? And in this case, we don't have anything that cancels, so we're done. All right. (32 x cubed y squared). We're going to take the cubed root of this one. Numbers, we have to do the prime factorization. So 2 goes into 32. Let's see, 16 times. 2 goes into 16 8 times, 2 goes into 8 4 times, and 2 goes into 2 2 times. Index says that we're looking for groups of 3. So we have, count off 3, and we have one group of 3, and then we have 2 remaining. So we know that we have 2 on the outside, and 2 times 2 on the inside is 4. Now, since we're dealing with our variables, we can take our roots. Take our exponents divided by our roots. So 3 divided by 3 is 1, so 1x will come out. But we don't have enough y's to come out because we need 3 of them, and we only have 2. So these 2 have to stay inside. And always remember, I almost forgot, we need to keep our index with it. And that would be our answer. Okay, for our one more complex, we have 16 x to the 13 y to the 15 all over 64 x to the 4th y to the 11th, and all this is in a cubed root. Okay, we could separate these, or we could leave them together. We're going to, let's go ahead and reduce what we can. We have some x's here. If we take 4 out of the bottom, we have 4 in the top, which is 9. Do that in a different color. Then if we take 11 out of the bottom and we take 11 out of the top, we get 4. So, rewriting that, we have the cube root of 16 x to the 9th y to the 4th over 64. Alright. Now it's time to find our factorizations. We have 16 and we need to find out how much will come out. So 16 divided by 2 is 8. Divided by 2 is 4. Divided by 2 is 2. We need groups of 3. So we have one group, 1, 2 will come out, 1, 2 stays in. If you take this one, divide, it has an exponent of 9, divided by the root of 3, we get x to the 3rd, because it all comes out. Here we have y to the 4th. We need to take 4 and divide it by 3, which we get 1 with the remainder of 1. So 1 can come out, but 1, since the remainder is 1, 1 has to stay in. And on the bottom, 64. We have, let's see, over here. Yes, 64, if we take 2 out of it, we get 32. 2 divided by 32 is 16, I believe. And then if you take 4 times 4 is 16, but we need groups of 3, so we have to redo that one. We take 2, that goes into 8, 2, 4, 2, and 2. So we need groups of 3. We have a group of 3 here and a group of 3 here. So we have 2 groups of 2, which we have a total of 4. Is what's on the bottom. And as always, when we get finished pulling stuff out, we have to check. And you can only cancel things that are on the outside with things that are on the outside. We don't have a cube root on the bottom here, so this is on the outside. So 2 will go into this 4 twice. So our total answer on this one is x cubed, y cubed, square root of 2y over 2. And that is our final answer. Got just a few more for this section. We have 54 x to the 15th y to the 12th all over 27 x to the 4th y to the 8th, and we're going to take the cube root of all this. If you notice, we could, I believe 27 goes into 54. 54 divided by 2 is, yep. We can reduce inside because it's all in the same index. We have a 2 here. Get different colors so you can see what's going on. On our x's, we have 4 on the bottom. If we take 4 from the top, we get 9. No, we get 11. Sorry about that. And we have 8 on the bottom, and if you take 8 from 12, you get 4. So rewriting that, we have the cubed root of 2, x to the 11th, y to the 4th. So now we can try to determine what's going to come out. We need groups of 3. 2 is already a prime factor, so we know that 2 has to stay inside. But we can, if you divide 11 by 3, oh, we get, what, 9? With a remainder of 2. So we have 3 whole ones that come out, and we're dealing with x's, so x to the 3rd. And then we have 2 that remain left inside. Now let's do our y. We have 4 of them. Divide by 3 gives, we have 1 times 3 is 3 with a remainder of 1. So 1 y comes out and 1 stays in. So there you go. Here's our answer. Because there's nothing to reduce afterwards. Here's our new problem. We're taking the cube root of 108 x to the 7th. We have to do our prime factorizations to find out what it's going to be. So if we take 2 out of it, we get 54. 2 goes out of that, gives us 27. 3 will come out of that, giving us 9. And then 3 times 3. Those are all our prime factors, or I learned it as a factor tree. You might have learned it that way as well. We're looking at groups of 3. We only have 2 2s, so we can't take a 2 out, but we do have a group of 3s. 3 3s, so we know that a 3 will come out and a 4 stays in, because 2 times 2 is 4. Now let's find out how many x's can come out. We have a total of 7, and we're going to divide that 7 by 3. So 2 times 3 is 6. And when we have a remainder of 1. So we have 2 x squared comes out, and we have to keep an x inside. That, ladies and gentlemen, is our answer. It's 3x squared to the cubed root of 4x. There we go. That looks a little better. And here are, then you're going to get some simple ones. We're just numbers. So 864 to the cubed root. Again, we're going to look for groups of 3 in our factor tree. So 864 divided by 2 is 432. Divided by 2 is 216. Divided by 2 is 108. Divided by 2 is 54. Divided by 2 is 27. Divided by 3 is 9. Divided by 3 is 3. Now granted, you could have took out 4 here and another 4, but since we're looking for an index of 3, it's probably best to go down as far as you possibly can to the smallest factor in the long run. It's a little more time consuming, but you don't have to go back and factor again like we did before. Again, we're looking for groups of 3, so we have 3 2s. Oh, we only have 2 here, so, and we have 3 3s. So 2 times 3 is 6. So 6 is coming out, and we have inside is 4. Because 2 times 2 is 4. And that is our answer for that one. One more is 125. The square root of 125. So if you take 125 and take 5 out of it, you get 25. And you take another 5 out of it, you get 5. Again, if there's no number here, we know it's a square root, so we're going to deal with 2. So we need pairs. We have 1 pair of 5s, so 5 comes out to the square root of 5, and that's our answer. Hopefully that was a really good review on how to simplify radicals.